Welcome to our third webinar in our 4-webinar series on achieving and improving reliability. This one is called Developing a Reliability Test Strategy Using Test Strength. Now, we all know that accelerated stress testing, we've said it before, the objective testing at subassembly and product level, not to damage our product but take our product out with the specification limits as far into the design limits as you can without destructing. Allows us to investigate via high stress level, decide which issues to resolve, etc., and move forward, stimulate defects. That's our overall objective. We know the bathtub curve is very common both electromechanical and electronics. The early life period is really the most difficult period to work with because there are so many potential weaknesses emanating from a process, from design, from weak components, etc. After the early life period expires, we go into the more intrinsic steady state, easier to predict. So really a lot more emphasis must go on to how we manage and perform our early life reliability stress testing and how we make sure that our test is indeed strong enough to stimulate defects. Now, when you develop a reliability test strategy, both patent and latent defects are introduced into the product. During manufacture, fabrication, assembly, handling and test. So these defects are waiting to happen. Right? The patent defects pass through various assembly stages till they're detected by a test or inspection of sufficient thoroughness and are then eliminated from the product, most often in the manufacturing process. However, a smaller percentage of defects, however, cannot be detected by conventional means. These are what we term latent defects. Now, latent defects are characterised very simply as inherent or induced weakness or flaw in a material that will manifest as an early or premature failure in the operational environment. And we call these as early life defects. Very different from traditional standard reliability. We're focusing very much on the early life period because the defect mechanisms are different and the type of testing we must do to stimulate them is also very different. And it's the early life defects which the accelerated stress test is designed to stimulate and to give best and maximum payback. Now, patent defects, basically parts, for example, that can be broken or damaged in handling, maybe the wrong part's been installed, electrical overstress or ESD causing a failure, missing parts, interconnections, open wire due to handling damage, wire short to ground. These things are generally found in some form of functional testing on a manufacturing line or at the end of the line or a quality test, etc. But latent defects generally can't be detected till they're transformed into patent defects. This is done most easily by environmental stress applied over time, and the stress testing is the vehicle by which the latent defects are then transformed into detectable failures or patent defects. In parts, it can be partial damage through electrical overstress. It can be physical damage during handling, which hasn't caused an actual full failure. Material or process-induced hidden flaws. Maybe damage inflicted during soldering operations with excessive heat. Or interconnections, cold solder joint, inadequate solder, broken wire strands, loose screw terminations, improper crimps. So these are the kind of defects that our early life reliability test program really should to find. Now, as we go on to try and develop a reliability test strategy, the emphasis on early life testing will be using modern stress techniques. Random vibration is very good, thermal cycling is very good, perhaps following with periods of elevated temperature, incorporating power cycling for more voltage defect stimulation. These can be up to 90% effective in finding early life defect mechanisms if the stress testing is planned correctly for the sufficient time with the right stress levels. Now, test strength modelling enables the reliability engineer to design the most effective early life stress test. This is not a long-term accelerated life test. Early life with high probability of stimulating early life defects. The Hughes aircraft study concluded very clearly many years ago that random vibration and thermal cycling are most effective. And the test strength models they developed were also used to describe test effectiveness for other stress types, power switching, constant power, and also constant high temperature. So we have all at hand to be able to look at our early life test, model it for test strength. If the test strength is too weak, the detectability of early life defects will be low, so we need to find ways to increase that and then remodel it. But it's a great tool for modelling our early life test programme. Now, when we're developing the reliability test strategy, a number of different studies have been done by many organisations. This one basically shows a weighted rank on the Y scale against the type of environmental stress, essentially stating which are the most effective stress types in finding early life defects. Here we show thermal cycling as top, random vibration, high temperature, electrical stress, thermal shock, etc. So clearly, the Hughes study done many years before this was pretty much in line with that in terms of thermal cycling, random vibration, high temperature and electrical stress being the most efficient. The key to this is how to combine them and then also how to measure the test. Another study was done in France by a major reliability group, again showing you can tell by the area of each circle, temperature cycling, biggest, vibration, humidity, thermal shock, power cycling. There's some overlap with the defect types, but basically again that's showing similar. So therefore we are definitely doing the right thing by focusing on temperature cycling, vibration, power cycling, maybe thermal shock, and perhaps elevated temperature with humidity, albeit there's no test strength model for humidity. But all in all, it makes it a lot easier to us to focus on the right type of early life reliability. Now, as we develop this typical test profile, a real life case study from a major electronic manufacturer, what they were doing was 30 minutes random vibration, 36 hours thermal cycling, 60 hours elevated temperature with power at 40 degrees C, and incorporating some power switching. On the face of it, for an early life test, they used that to try and stimulate the first 30 days type defects. And on the face of it, it would look pretty powerful, looks good. But when we look into this, then we see things are a little bit different. If we look at the basic thermal cycling test profile in more detail, we can see this particular manufacturer does 6 thermal cycles minus 20 only to 50 and 8 thermal cycles minus 10 to 40 degrees C. On paper that may look fairly effective for doing a first 30-day early life reliability simulation test. They also do random vibration, which has its own test strength values, and they can be taken from the mil standard 344 or some fixed values which were also set in the Hughes equations. If we look here at the test strength of the thermal cycling, we see the Hughes thermal cycling test strength model here, and we go through each point. N is the number of thermal cycles, we know that. Delta T is our temperature change, the thermal cycling temperature change measured at component level. So we know that the components are changing at 1.5 degrees C per minute during their thermal cycling between the lower and uppermost temperatures you see. And T, we work out the modulus of T with that equation. So we can put everything in there and quite easily work out our test strength for these profiles. Obviously pictures here show how to measure, use thermocouples to measure the component temperature change rates. Obviously the oven in which it's sitting in may change at 4 or 5 degrees C per minute air temperature, but because of mass of the product, clearly that is slowed down, and therefore you must measure the effect on the components to get a true measure of thermal cycling test. We then look at the profile and we can see the lower and uppermost. This is of another product altogether, and we can then determine our change rate on the components and the lower and upper temperatures which the components or the sub-assemblies actually achieve. Now when we go back to those equations of the 6 and 8 thermal cycles, both the same temperature change rate but different upper and lower temperatures, we see it's pretty small. So we see basically they're both averaging around about 5%. So not too high. So 5% means really there's only a 1 in 20 chance of stimulating a latent defect with that thermal cycling. On elevated temperature, the Hughes equation also can be shown quite easily, and it's an exponential model, and T is our test time in hours, and in that profile they did 60 hours. T is our elevated temperature, and obviously that gets converted into degrees Kelvin, and when we calculate that it comes out as only 4.2%. So again, fairly low. Now for continuous power on, the Hughes equation also has a model, T over T plus C. C is constant at 900 and T is effectively the power on time duration, and here it was 60 hours, so 60 divided by 960 gives us 6.3%. Power switching has its own model, and we can see that quite simply. Again, C is the constant of 900, T is our power on time between switches, and N is the number of power switches. In this case, there was power switching every 2 hours, so we can see 900 divided by 902. There was 27 power switches in the 60-hour profile, and we get, as a result, almost 6% test strength. Now, how do we combine all the test strengths? Well, clearly we can't just add them, because if you did so much testing and you added them, it could get to more than 100%, which is clearly ridiculous. So we look at this in terms of a probability law. What we're doing is we're saying, well, the overall test strength is equal to 1 minus the probability of not finding a defect with the testing. So if we look at that, the probability of not finding a defect with everything combined, then would be the probability of not finding a defect with test strength for cycling, temperature cycling 1, cycle 2, elevated temperature, constant power, and power switch. So it's probability law. So we are going to multiply the probability of not finding a defect from each applied stress, and then we come up with a figure which we then subtract from 1. Now, as we show that then means that we have only got 24%, so a 1 in 4 chance of detecting or stimulating latent defects in the early life period with this particular profile. So very low. On the face of it, the profile looks pretty good. There is a lot of different testing, but when you look at it in reality with the test strength modelling, very quickly we see it's inefficient and unlikely to really achieve much. If we wanted to add random vibration, if the test strength was 40%, then again we apply the same probability law. Probability of not finding a defect at random vibration is 1 minus 0.4 or 0.6 multiplied by 1 minus 0.24, i.e. the probability of finding this is not finding a defect with all the thermal work, and therefore we then increase that to 0.54, so we take it up to 50%. Much better, but clearly the profile they're using needs a lot of focus and improvement if they're going to be successful in stimulating the first 30-day period defects. Finally, measuring test strength, we can also use that for setting ESS, environmental stress screening, which is still done in a lot of military products, a lot of aeronautical products still do 100% ESS, and it's important. They all use thermal cycling, and it's very important to then use test strength to understand how effective it is. On the face of it here, we see minus 3 to 70, but because the temperature change rate is only 1.3 degrees C per minute with 10 cycles, we get a test strength of less than 10%. It's pointless spending a lot of money doing a 24-hour ESS on a product like that. You have to change it radically, and the test strength modelling is a great way to set a standard for test strength level. It might be 0.7, it might be 0.8, to achieve that on everything you do in early life testing or ESS. So all in all, without using a test strength model, we really have no way of measuring the potential effect of stimulating defects from our reliability stress testing, and as a result we would go back the way, and we would then be scratching our heads on wondering why we never found defects. The test strength model answers that question. I'd like now just to finish this presentation, and effectively we will happily take questions, emails, etc., and we'd be more than happy to go into this in more detail with anybody who was interested in this. Thank you very much.